Next, we're going to look at analytic samplers, which are both extensible and scalable. We start out with a simple mathematical concept that we'll look at in some detail. So our starting point is a combinatorial class with an ordinary generating function a of z that's got a radius of convergence x0 that we know, and a positive number x that's within the radius of convergence. So for every element in the class, a of z is the sum of z to the size of the element. So what we're going to work with is called a PowerSeries Distribution. It's actually a very old concept, goes back to 1950. PowerSeries Distribution at x for a, for the class, assigns to each object the probability x to the size of the object over a of x. Very simple definition. And it's got some useful properties. First of all, the distribution is spread over all the objects in the class, not just of a particular size. So if we sum over all the objects in the class, then we get 1, spread over all the objects in the class. As with many other examples of using OGFs in analysis of algorithms, if we just collect according to objects of a particular size, all objects of each size have the same probability, x to the size. And so that's another way of writing the generating function. And it's pretty easy to calculate the expected size of an object drawn uniformly from the whole distribution. So expected size of an object at x is the sum over all the objects, the size of the object, x to the size over a of x, and then just recalibrate by collecting together everybody of the same size, and we get that simple formula, which is x a prime of x over a of x. So easy to calculate the expected size of an object drawn uniformly from a power series distribution. So that's the basic object that we're going to be working with in this subject, in this section. So an analytic sampler, we start with a class and its OGF and the radius of convergence, and that's a standard process for symbolic transfer in analytic combinatorics. What we want is a program that returns objects drawn from a power series distribution for the class. That's called an analytic sampler. That is, it returns each object with probability x to that object's size divided by a of x for our given x within the radius of convergence. And the idea is that we can derive the sampler directly from the specification and the generating function. So here's the easy cases. We need a sampler and we need a proof that it samples each object A with probability x to the size over a of x. So the neutral class, that's epsilon. The sampler is just return epsilon. There's one object of size 0. And the OGF is 1, so and x to 0 over 1 is 1, so that's the proof that we have the proper probability. We return the empty thing with probability 1. And similarly, the atomic class, there's one object of size 1, the OGF is z. The probability that that object is sampled is x to the 1 over x, which is 1. Again, that's an easy case. Now what we want to do is build on that for the other combinatorial constructions that we typically use. For example, disjoint union. The analytic sampler for the disjoint union of two combinatorial classes is just flip a coin with probability bx over ax. Comes up head, return B, otherwise return C. That's the disjoint union. And here's the proof that each object is sampled with the proper probability. If you want to compute the probability that an object belongs to B, you just sum over everything in B, x to the size of that over a of x, but that's exactly B of x over a of x. So that analytic sampler exactly matches the needed probability. And for Cartesian product, we're going to compose the B and the C into a single object somehow, depending on the class. And again, we can develop an immediate proof that each object is sampled with the proper probability. Since they're both included, x to the size of a over a of x is the same as x to the b plus c over a of x. But the generating functions we know from analytic combinatorics, a of x equals b of x times c of x, and then we can split it out and we're multiplying the probabilities. So again, the proof that each object in A is sampled with the proper probability is quite straightforward. And this immediately gives the basic table for building an analytic sampler. For the disjoint union Cartesian product constructions, we have the program that we're going to need, and for the neutral and atomic class. Now let's look at an example like random bit strings without long runs. So let's say no runs of 4 straight zeros. And again, in earlier lectures, well, lecture 1 of analytic combinatorics, or earlier lectures of analysis of algorithms, we have a simple combinatorial construction. That class is z less than 4 is empty, single zero, 2 zeros, or 3 zeros. And that's composed with either the empty string or a 1 followed by a B4. That's a combinatorial specification and leads immediately to this generating function equation that we've seen before in lecture 5 of analysis of algorithms. And then if we take the rules for generating a sampler, in this case our compose operation is concatenation, we immediately get this recursive program. So this first is just an implementation of the generating function, denominator of the generating function, to cover this use of the union operation. And we immediately get a recursive method that says flip a coin with probability 1 over b4 of r, and if it comes up heads, just return one of those early strings with equal probability. Otherwise, you return one of those followed by a 1, followed by a recursive call to generate another string. Simple recursive program. We're going to have to look some at its properties, but one can see how from a spec we're going to pretty automatically get a program. And we'll look at another example. But the critical question about a sampler of this sort is, what size object does it generate? If you study this code for a little while, you're going to see, okay, well, it's going to depend on the value of r, and it's going to be a random variable because there's a lot of Bernoullis in these calls. But the thing is, the whole essence of the construction is, whatever the length is, whatever size object it returns, it's going to be uniform. Each string of that length is equally likely to be the one returned, and that's what's most important to us. So what we want to do is, we have the flexibility to choose any value of r less than the radius of convergence. What we want to do is choose one that'll give a particular expected length that we're looking for. So what's the expected size of the generated sample? Well, we did that calculation. It's drawn uniformly from a PowerSeries distribution, so the calculation that we did before for the expected size holds exactly. So for string with no 0 to the 4th, that's the generating function. We know from analysis that it's asymptotic to constant over 1 minus beta r with that particular value of beta. Calculate the derivative, calculate r times the derivative divided by b of r, and we get this simple formula for the expected size of the generated sample. So 1 over beta of r is about 0.51875, and if we plot the expected size, we're going to see as r gets close to the singularity, 1 over beta, it starts to grow up. The action is really close to that singularity. Just keeping that in mind, still, we can generate a sample of expected size n by choosing the value of r such that n is equal to that expected size. In other words, for this case, we take n equal to this thing that we calculated and solve for r. And it's n over n plus 1 times beta. So using that value for r is going to give us expected size n for any n that we might want. That's the code that implements that if we want to generate a bit string with no 0 to the 4th of expected length n. Now, it's important to note that in this case, the variance is not small. And you can go ahead and calculate it in the same way that we calculated the mean. And in this case, here's what goes on. So this is 10,000 trials trying to get a string of size 10,000. We get a bunch of short strings. We get about 1,000 strings close to where we want. And we get a bunch of strings that are way longer than what we want. And this is typical for analytic samplers. And we'll see in other examples what we get. Now, so in other words, the bad news is that a lot of the strings are short, but that's not really a problem because they're so small, so it doesn't cost that much. Now, also, some of the strings are really long, but that's also not a problem because there's not too many of them. But even more important, we can use rejection or anticipated rejection to limit the cost. So those are practical considerations that we're going to add on top of our analytic sampler to get an efficient method that does what we want. And the bottom line is that the total cost is going to be linear. This approach was laid out in another very important paper by Disjoint, Flageolet, Louchard, and Schaefer called Boltzmann Samplers for the Random Generation of Combinatorial Structures in CPC 2004. So the fundamental idea of this paper was we could get automatic generation and scalable, so we can get huge structures if we want. What we do is use rejection to wait for an object of desired size, since the size of the object is a random variable. We use anticipated rejection to make sure we don't get huge objects. And again, very important part of every Flageolet paper is a complete analysis using complex analytic methods of analytic combinatorics that completely tell us the performance of these samplers. There's a full characterization of 3 different types of size distributions that might show up depending on characteristics of the combinatorial class in question. And there's a theorem that says that any decomposable structure has an efficient sampler that produces objects close to a desired size, with each object produced equally likely among all objects of the same size. We have to modulate the term efficient a little bit because the paper assumes that there's an oracle that can evaluate generating functions efficiently. And that can be a stumbling block in some modern implementations. But still, this is an extremely important and significant paper. Now, we've been using the term, and we will consistently use the term analytic sampler as being equivalent to Boltzmann sampler to avoid confusion with other uses of the word Boltzmann in the modern literature. Okay, so the summary for analytic samplers is we can derive Java code from construction pretty much immediately, compute the value of R that gives the target size. We need to use global variables on the size under consideration to avoid recomputing things and to implement rejection. And we're going to use anticipated rejection to avoid large sizes. So this is our full sampler for generating random strings with no occurrence of 4 zeros. And in the recursive routine, we test if the string is getting too big. And in the initial call, while we're waiting for the target size, we test whether we're in 10% of the size that we need. So that's the rejection, anticipated rejection. And this is a very fine method for getting long random strings with no 0 to the 4th, and it works in linear time for any value of n. Quite useful idea that expands to any constructible class. So let's look, for example, at random binary trees. So again, that's our construction, that's our generating function. And again, the rules give us pretty much immediately a pretty simple sampler. Generate a node, generate a left subtree and a right subtree, and then stop with, by flipping a coin with a value given by the generating function, just applying this union rule for that plus. Very simple recursive program. And so again, we have to choose the value of R that gives us the target size. And for random binary trees, it's even more extreme, as it's 1/2 plus 1/2 squared to 1 minus 4R. As you get really close to the singularity, the size starts to shoot up. And then we can compute the value of R to expect a tree of size n. And actually all we need is R over T of R, and that's just 1 over 2 minus 1 over n. And boom, we can get a big binary tree within a certain range. So again, that's the code to generate a tree with n nodes on average. But again, we need to use rejection to wait for a tree of a specified size, and anticipated rejection to avoid huge trees, and then we get a linear total cost. And in this case, the distribution is such that we get a pretty huge number of small trees. And if we don't do this rejection stuff, we might get a huge one. In this case, looking for a tree of size 1,000, we produced a tree of almost 1 million nodes. So we don't want to do that. So one idea, extra idea is, well, we're going to do this rejection stuff anyway, so we don't have to be precise about the value of R that gives us exactly n. We might as well just use the singular value. In this case, we might as well just use a 4th, which gives R over TR equals 1/2, because for very huge n, it's going to be so close to a 4th anyway. And then we just use anticipated rejection to make sure that we don't get that huge tree. And then when we generate, we just look for a tree inside the target range. And again, with those two changes, it's going to be linear time. So this is looking for a tree of 10,000 nodes. In one case, we found it in 25 trials. In another, we found it in 1,200 trials. But the critical point about this is that this easily extends to other types of trees and other classes. Use the generating function and the construction to get the recursive program, and just use the singular value and these rejection techniques to get all different types of things. So this is a random binary tree, random ternary tree, random 0, 1, 2 tree, random 0, 2, 3 tree. Very easy to get all types of random trees with this technique. Now, going back to an interesting computer science part of the calculation, that recursive method, you might be called depth first. There's an equivalent sort of breadth first method called the Gulten-Watson process, where we do the calculation from the bottom up. It's a little similar to Remy's representation, but even simpler. So we're going to use a parent link representation for the tree, and we're going to have a queue. And the ith entry on the queue is going to be the parent of I. And what we're going to do is go through, and for each node, we're going to generate k children with a particular probability p sub k. Now, to calculate these values pk for different types of trees, we're going to need analytic combinatorics in general, and that's beyond the scope of this lecture, but it's motivation for studying analytic combinatorics. Again, we'll use the upper bounds and tolerance to terminate things. But for example, if you use P0 equals P2 equals 0.5, you get binary trees. And it's an extremely simple calculation. So let's start this way. So we start with root 0, and then we're going to generate with probability 1/2 either 0 children for root 0 or 2 children for root 0. In this case, we generate 2 children for root 0. And again, using a parent link representation, this says that the parent of 1 is 0, the parent of 2 is 0, as in that tree. And now we just move through. We're done with 0, so now what about node 1? And again, let's say that the random process gives us, let's do 2 children for node 1. Now 3 and 4 are going to be the 2 children for node 1, and 3's parent is 1 and 4's parent is 1. Very simple. So whatever node we're on, either we generate 2 or 0 children. In this case, we do another 2 children for node 2. Again, the same idea. 5 and 6, their parent is 2. But now when we get to 3, we come up with 0 children, so we don't do anything, we just move on. We get to 4, 0 children for 4, we just move on. In this case, we get to 5, maybe 5 has 2 children. And now we get to 6, 7, and 8, no children, and then we're done. So that creates a tree. That's a Gulten-Watson process. Depending on the probabilities, you're going to get different types of trees. And it's amazingly simple code. So we start with a Q, and we put 0 on it. And as long as we're not done, we're done when we're past the size of the tree. We have no more nodes to deal with. We generate K, the number of children to put on, according to the discrete distribution, like the one that I gave, P0 goes 2x a half, and then just put the current thing on the queue. That's it. Extremely simple program. In fact, I have to confess, I generated all the trees on the previous slide with this code. That's what these probabilities are. P0 equals P2 equals a half gives binary trees. P0 equals 2/3 and P3 equals 1/3 gives ternary trees. And have them all equal to 1/3 gives 0 and 2 trees. And 5/9, 1/3, and 1/9 gives 0, 2, 3 trees. And again, to get these, to map these tree specs to these probabilities, amazingly requires good analytic combinatorics that we'll get to later. So these are trees with 500 nodes. And they also, regular analytic sampler works. This is just a computer science trick that is very neat. Okay, so for what about labeled classes? Those are unlabeled classes. Well, the same types of rules work for labeled classes. Some of these work for unlabeled too. We can describe more complicated operations like sequence. If we have A is a sequence of B's, then we generate an integer K according to a geometric distribution, and then we compose K independent instances of B. For set, it's almost the same, it's just a different distribution. We use a Poisson distribution. And for cycle, we use a so-called log series distribution. Those are the rules to build a sampler for labeled classes. If you actually need the labels, you just apply a random permutation to all the objects at the end. And I'll give a couple of examples. So here are these distributions for labeled classes showing how to compute them. They're easy to compute iteratively, and they're classical. And all of these are PowerSeries distributions. And really easy to apply to build analytic samplers for labeled classes. So, for example, a permutation is a set of cycles, and that, again, is one of our classical examples of analytic combinatorics from Lecture 5 of Analysis of Algorithms, and immediately puts forth this sampler where we generate a queue that contains cycles. And how do we get it? We do a Poisson with a value that's derived from the generating function. And then we put that many instances of a cycle. And how do we get the cycle? We do a log series. So the constructions immediately give the code for analytic sampler. And again, we have to choose the value of R that satisfies the size, and the calculation is straightforward. And so that's going to give us a random permutation. And these are 4 random sets of cycles with about 200 nodes. Again, from a pretty simple recursive program. But really the power of this method is that it's very easy to add restrictions of various types. Like if we want a set of cycles where the cycle lengths are taken from a particular set omega, like if we want to be involutions, it'd be size 1 and 2 and so forth. Just take that same code and before you put a new cycle in the set, you test if the size is in omega or not. Now, there is a difficulty in computing the right value for R in this case with our use of rejection. It, in this case, works to use the same values for unrestricted cases. But in general, that can be a difficulty in applying this method. And so what this allows us to do is generate sets of cycles with size restrictions. So this is permutations of about 200 nodes where the cycle lengths are all between 20 and 50. Or this is 100 nodes with between 5 and 25, or 50 nodes between 5 and 10, and so forth. There's lots of applications where these sorts of restrictions make a lot of sense. And again, whatever we get, it's uniform, it's of equal probability to appear among all objects of the same size. And that can be a very important factor. And we can extend it even further to mappings with restrictions. And actually, the breadth-first approach works for mappings. Rather than put a node on that queue at the beginning, I put cycles on there, and the same code, pretty much the same code works. So these are mappings of 1,000 nodes where everybody's got in degree 1 or 2, and there's no small cycles. And again, an amazing variety of large combinatorial structures that we can get with very, very simple code. So just step back for a second and look at recursive method versus analytic sampling. So the recursive method, we did have pretty simple code, recursive code, to generate an object of the specified size. The problem is the excessive preprocessing time and space that really depends on the size of the object that we want to generate, which can be prohibitive. With analytic sampling, we don't get the exact size, but we can get about the right size. And we have very minimal preprocessing time and space because it depends on the size of the spec, not the object, which is much, much smaller. So there's 3 key ideas that are important to carry away from this. First of all, both of these methods immediately can handle variations and restrictions. They're automatic. In recursive, we've got industrial strength automatic sampler generators of various flavors. They can automatically be built from the specs in principle, but the difference is that analytic samplers are scalable. All we need to do is relax the size constraint. So with analytic samplers, we can generate huge instances of all sorts of combinatorial objects. And here's some examples. So this is called a skew plane partition. That's about size of about 1 million. This is a cactus graph, which is a particular kind of graph that arises in plenty of applications. These are so-called polynomial tilings and scientific problems that these things relate to. And this last one is a so-called reluctant random walk. Again, completely different types of combinatorial structures, but we can generate big random ones and study their properties. With analytic samplers, we can study anything that can be modeled as a constructible combinatorial class. So that's our summary. Analytic samplers based on PowerSeries distributions are effective, extensible, and scalable. I haven't done the rigorous analysis in this lecture, but in many, many situations we're able to completely prove lack of bias and scalability, and we can generate huge random instances and open up new areas of scientific inquiry. Going back to Turing and before, This enables a scientific approach to discrete models. We formulate the model of whatever natural phenomenon it is, that is, develop a specification. We can collect instances from the real world. Then we can develop a scalable sampler and generate random instances and test the model by validating that the real instances are similar to the random ones. And that's an extremely effective way of mode of scientific inquiry nowadays. The process is not completely fully automated in the case of analytic random samplers for huge instances, but we're very close. It's an ongoing research goal. And that's just the beginning. People are also starting to study non-uniform samplers based on multivariate analytic combinatorics. It's a very rich area of research that already has seen many successful applications.